In this video, we are going to be talking about the nature of data. If you understand the nature of data, you know what kind of questions you can answer and which types of algorithms are suited to achieve good results. Good is a subjective word here, I know, but we will talk about what is good and what is not good in another lecture. So think of all the most common types of data that we encounter since we are children. For instance, categories and fractions. Those are some very simple types of data. All of us are fairly familiar with those types of data from a young age, and we have a good intuition for them. The types of data that you work with can be really critical, and it influences all steps of the data science life cycle we have talked about in the last video, starting from problem formulation to deployment and monitoring, and so on. It influences data collection, storage, the visualizations we can do, the models we can apply, and the list continues. But now let's look at different types of data. For a decade or so, we have heard the buzzword big data. Companies have been collecting data for years. A lot of them have used the data to improve their processes, their algorithms, their revenue, and so on. A lot of them, surprisingly, are sitting on a lot of data without using it really. And then that data becomes redundant. Companies even forget about it sometimes. So they are not really adding value, but just collecting more of it. So a lot of the time, it's better to stick with what we call smart data. It is not a term I invented. It is bio-inspired and has been used for years already. And it really means to have the most important attributes of the data available rather than a lot of noisy data. Data plays a big role in the Industry 4.0. We have now faster networks, larger storages, new sensors all the time. There is a massive amount of data available, but how do we make it more valuable? That's the question. Remember from our last video, the idea is to create value from data, both in science and in business. We've talked a lot about these terms, but now let's define big data. So big data means vast amounts of data. Think of both structured and unstructured data, which is characterized by 4 key elements. 2 of them are volume and variety, which are self-explanatory, and we again all have a good intuition for them. But the other 2 are a little bit more special. And even though you know the words, let's discuss them each individually in this context. So the first of them is velocity. Now everybody knows what velocity is, but what does it mean here? It means the speed at which data is generated, distributed, and collected. The velocity rate is influenced by different things like the amount of sensors present in a data ecosystem, the enabled devices, for instance, at a particular moment in time, and the amount of individuals using the internet at a particular moment in time, for instance. Now, if we look at the other one, veracity, this means how reliable and how significant data really is for the problem you're trying to solve. So it is essentially the quality of the data, and it's influenced by factors like where it has been collected, how it was collected, and how it will be analyzed. So the question is, do we want big data or do we want smart data? Well, in my opinion, smart data is a lot of the time better than big data. Now let's look at more types of data. So we have qualitative data, which is oftentimes called also categorical data. This kind of data consists of variables that assess a specific characteristic or a quality. Most of the time, it is represented by text, but also often it is encoded in numbers. Let's take an example. A good example of qualitative data is, for instance, marital status. Somebody is married or not married. This can be coded also with numbers if necessary. For instance, 0 for married and 1 for not married, but it's still categorical data. So there are 2 types of categorical data, nominal and ordinal, and let's look at both of them in this table. By definition, nominal data usually groups into distinct categories without any inherent order or ranking. So an example here are colors, marital status, favorite band, and so on. Ordinal data categories data into ordered or ranked categories with meaningful differences between them. So here we can look at customer satisfaction rating, grades of a student, level of income. For instance, we can have low, medium, high level of income, and so on. When we talk about mathematical operations, there are really no meaningful ones for the nominal type of data. But for the ordinal type of data, we can think of median, for instance. When it comes to order ranking, there is no meaningful order really for nominal data. But for ordinal data, categories that data is ranked into have a specific order or a specific rank, but the difference in magnitude may not be uniform. If we look at central tendency next, here we have for nominal data the mode, which is the most common or frequent category. And for ordinal data, on top of the mode, we have the median. We cannot talk about the mean really because of the variable magnitude between different ranks. Now, if we look at use cases, for nominal data, we have object classification or data aggregation, for instance, through clustering. And for ordinal data, we have rating survey responsive, grades of students, and so on. Now that we looked at qualitative data, let's look also at quantitative data. So quantitative data usually describes either phenomena or properties that can be measured or counted. These are examples like distance, temperature, height, etc. It is also called numerical because it is always represented by a number. This type of data is very broad, but two subgroups here are very important, and they are listed here, discrete and continuous. So, if we look at their definitions, discrete data consists of distinct values, usually whole numbers. Continuous data can take a value from within a given interval. Some examples here. So for discrete data, we have number of students in a class, population, coin toss outcomes, amount of customers, and so on. Continuous data, some examples are height, weight, temperature, and so on. But to give you a little bit of intuition here, let's look at the nature of data. So for discrete data, we have whole numbers or counts of items, and they're often measured using integers. In continuous type of data, we have a continuous spectrum, so there are values within this continuous spectrum. It's usually represented with a decimal number or a fraction. The mathematical operations we can perform on discrete data are counting or summation, and on continuous data are arithmetic operations, which result often in decimal numbers, fractions, and so on. If we look now at probability distributions, so a discrete probability distribution counts occurrences that have countable or finite outcomes. Discrete distributions contrast with continuous distributions, so for continuous data, where outcomes can fall anywhere on a continuum. Common examples of discrete distributions include binomial, Poisson, and Bernoulli. In continuous distributions, we have the normal distribution or the student distribution. The use cases essentially for discrete distributions are counting occurrences, while for continuous distributions we have data, we have measuring quantities, analyzing measurements, and so on. But things are not as simple. Most of the time, things are a little bit more complicated than that in real life. Imagine you are working in a data science team, and one day you have a client who comes with a huge Excel sheet in which there are 10 sheets or even more with tables, each with hundreds of thousands of rows. Assume this client is a hospital and each line is a patient. That kind of data, so patient data, include a lot of data types that we previously mentioned. So for each patient, we can have age, marital status, gender, blood pressures, different values of different biomarkers. We can have links, for instance, to imaging of different body parts, of tumors, and so on. Also, a great example of the mixed data are images, or even better, video footage. So these contain different categories of objects, sorry for that, but also a lot of numerical data and pixel info and metadata and so on. But that is not only the only important aspect. We can also have high dimensional or low dimensional data. So in high dimensional data, we have, for instance, images, like the example we had before. For humans, everything that is higher than 3 is high dimensional data, essentially, because we can see only in 3 dimensions. So if we add already time, it is quite difficult for us to perceive it in a good way. But these terms, high and low, are a bit subjective. There's no clear definition where high starts and where low ends. However, some cases are painfully clear. As you figured out by now already, and hopefully from the examples before, dimensions are essentially the attributes of the data that are often, or all, if not all the time, called features in data science and in machine learning and in AI and so on. But now what does this curse of dimensionality really mean? As we add more dimensions and more features to the data space starts to increase exponentially, and the data becomes sparse, very vast. And this can cause a lot of problems. Applications become more computationally expensive, and as a result, of course, also more financially expensive. Another issue we will talk in future lectures are that models start to overfit. They become very complex and they start to fit rather noise than the actual data that we're feeding there. So they start to fit the noise in the data. And this essentially reduces the model generalizability. High dimensional data is also very hard to visualize. And we're going to talk later on in our lectures about how to reduce this dimension for dimensionality reduction techniques. But now let's look at some examples here. So on the right side, you have a video camera system over here. This system creates a range of data based on semantic maps, on point clouds, and all of these are high dimensional data, which contains all kind of dimensions, pixel data, and so on. Now, if we look on the right, on the left side of the slide, what you see here is a heat map. Maybe a lot of you already know this. This represents hierarchical clustering analysis of gene expression data from 96 patients with gastric cancer. Each of these rows that you see here represents an individual gene, and each of the columns represents a tissue sample, so essentially a patient. Each of these cells that are quite small in this heat map that is huge represents the expression level of a gene feature in an individual tissue sample, so in a patient. Now the red and green coloring in the cells show the high or low gene expression levels. And this is hierarchical clustering, so we see how they cluster together specific genes in these clusters. Now this is a clear case of high dimensional data. And with this being said, thank you for listening and see you next time.